Okay, I think we should start. So it's my great pleasure to introduce our colloquium speaker, Maciej Zgirski, professor at the Institute of Physics of the Polish Academy of Sciences. And Maciej will talk today about the Nobel Prize in Physics 2025, Schrödinger's cat gets bigger. A few words about Maciej. Maciej received his Master of Science degree with distinction at Warsaw University of Technology in 2003, then his PhD degree in 2008 at the Nanoscience Center, University of Jyväskylä. I think that's okay. And
yes,
Finland.
Yes, it's in Finland.
Yeah, in Finland. And habilitation also with distinction at the Institute of Physics of Polish Academy of Science in 2022. Since 2016, Maciej has been the head of Coolphone group at the Institute of Physics of the Polish Academy of Sciences. And his main scientific topics are thermodynamics of nanostructures at low temperature, stochastic thermometry with Josephson junction down to nanosecond resolution. So, Maciej, the floor is yours.
Okay, thank you very much. Thank you for seeing many of you in the audience. So today we'll talk about today's this year Nobel Prize, and we'll try to see how big can be an object still to present quantum effects. That is why I gave this kind of the catchy title, Schrödinger's gets bigger. So this is because this year Nobel Prize was awarded for discovery of macroscopic quantum mechanical tunneling, and the macroscopic is the word which we need to underline here, and energy quantization in electric circuit, which is also macroscopic. So somehow, if these two hallmarks of quantum mechanics are met, we can say that we made another step to present quantum phenomena at even larger level. So this was awarded to three scientists. John Clark, who is very well known for development of squids, superconducting quantum interferometers. Michel Devoret at that time was his postdoc in Berkeley, and John Martinez was his senior PhD student. Okay, and we go to the core of our question. So the first time this question was posed by Erwin Schrödinger in his paper in 1935, he considered coupling of macroscopic cat living creature to a poisonous dispenser, which could be activated with decay of radioactive nuclei. And at that time it was known that this radioactive nuclei can be in superposition of states. It can be either in state before the decay and after decay. So it was then proposed by Schrödinger that by coupling this decay to some poison dispenser, we could be able to place also the cat in superposition, which would follow the superposition. It was being superposition inherited from the superposition at this microscopic level. And this was at that time treated as a paradox. Then people realized that there is a huge role of environment in the cohering, and the macroscopic objects, they quickly collapse towards the classical behavior. But anyway, it initiated this race for observing the quantum phenomena at even bigger objects. So what are these quantum phenomena that we can talk about? So this is a bit, okay, the popular science introduction, but just to recall you, okay, we have quantization of energy. Just think about hydrogen atom with different orbits, different orbitals, each having well-defined energy. We can do excitation on absorption by emitting or absorbing a single quanta of energy, which are photons. So in case of hydrogen atom, it happens for visible light or for ultraviolet photons. And this is, okay, known from time of Bohr, yes, from beginning of 20th century, that such quantization happens in atoms. But also for at the macroscopic levels for particles and atoms, we observe, we know that they have delocalized nature. If we look at harmonic oscillator, we know that it has the particle undergoing oscillation, quantum oscillation, its position is not well defined, but it is blurred in space. So we can find it in different location with different probability. So there is this delocalized wave nature, which also gives rise to leaking of the tail of the wave function out of the local minimum, and this leads to tunneling. So tunneling can be solved within mathematical equation of Schrödinger. So something which has no chance to go through barrier because it has too low energy can leak out through the barrier. So yes, this is the very this effect lies at the heart of quantum mechanics. Then we have superposition of states. So molecule can be at the same time. Say if take ammonia molecule, the nitrogen can point down or can point up, and we can have at the same time such superposition. Not only when we look at this molecule, we can then find whether it is up or down. And we have also, we know that atoms can decay. So this is here, I depicted the radioactive nuclei of the radioactive decay of uranium-238. It decays to thorium with emission of alpha particle, which is charged, which is nucleus of helium-4. And for this decay to happen, the alpha particle must escape through the atom through tunneling. On one side we have the Coulomb repulsion, on the other side we have strong nuclear forces. So the alpha particles escaped strongly here by the rest part of the nucleus, but at times, very rarely, it can make it through and escape. So this is tunneling. So the half lifetime for sample of uranium is 4 and 5 billion years. So it is very slow process. Yes, this is example of tunneling. But another well-known example of tunneling is nuclear fusion in the sun when two protons they fuse together into deuterium. This is in principle the beginning of the proton chain. And it happens, if you look at the numbers, this is very unlikely that two protons colliding together can form deuterium. Only in one event in 10 to 28 results in fusing two such protons. And this is again described by the phenomenon of tunneling. And this is responsible, so we have this Coulomb barrier. Protons cannot approach each other because they repel each other with Coulomb forces, but because they are quantum particles, their tails, they very slightly overlap, and this gives rise to this binding which eventually may happen. So this process is responsible for maybe not very slow, but also not very fast burnout of the fuel in our sun. That is why this, in principle, these reactions tells us that we have the fuel should be burned in roughly 5 billion years. Yes, but this is another example of tunneling. We have also the very maybe the closest to our labs, the example of tunneling when we have two piece of normal metal connected through insulating barrier or through gap of the vacuum. This happens in scanning in the scanning tunneling microscope, when the metallic tip probes the surface density of states, density of states of the sample through very tiny narrow gap, so we measure the tunneling current. Okay, we have this quantized energy orbitals that I was talking about. So you know there are these S, P, D orbitals, each with definite shape, and we in quantum jump, when then the photon is absorbed, we can get transition from 2s to 2p. Okay, orbital, and then it only happens when the properly matched photon can be absorbed or ejected or released. We have this quantum superposition, which is for example, for ammonia molecule. This is a very interesting lecture by Feynman from volume 3, chapter 9, when he describes by this superposition the opportunity of obtaining amplification, stimulated emission of microwave amplification by stimulated emission of radiation. So this is basically, it lies at the heart of the Maser operation, which is analogous to laser. And all this is possible because, yes, the theory which was built for describing the effects relies on the opportunity to converting in the deterministic way the wave vector of this molecule from this state to another on the Bloch sphere, yes, with the superposition on the way. So we go from 0 to 1, but we circle around all the possible superposition in this deterministic evolution of the wave vector as we irradiate these molecules with the coherent source of microwave photons which match the transition. Okay, this is the localization in the harmonic potential, which will be important for us today. So this localization happens in real space here. So we think here usually about normal particle. I mean in the coordinate space. But today I will try to make you think that this can be some other variable. We will call it some degree of freedom, and particularly it will be the superconducting phase, which I will show you is macroscopic variable, and the wave function describing the system will be blurred, not in this real space, but in the space of the superconducting phase. Okay, and now, so this was just kind of short introduction to these effects which we observed with particles at the single particle level, at that atom level. But the question which we pose, which was also posed by the Leggett, I think first time in 1978 in his paper, can macroscopic objects, so consisting of macroscopic number of particles, behave in a quantum way as if they were a single particle? So if this happened, we could talk about some artificially engineered atoms, which we could possibly use to some application or to present some new functionalities, but we could show that the quantum physics is not only limited to the very heart of the micro world. So can we find such a macroscopic system which would be described as a single wave function? So we need some collective state, okay, and we know that already at that time when these ideas were running in community, that superconductivity is a collective state and superfluidity. So these two phenomena, they seem to be a good candidates to investigate this issue. So what we have in superconductivity? Superconductivity, this usually what you see here, it is the wave function describing, this is plane wave function describing a single electron running in the crystal lattice. So we have the phase and we have some amplitude, wave amplitude probability that with the meaning that modulus square of it is the probability to find particle in this given place. But what happened during superconducting transition is, okay, in fancy words we tell that it's symmetry breaking, and this means that the phases which are completely randomized, each different for electrons, they have independent phases. They are not synchronized together. Now they decide to pick up a single well-defined value of phase, which is the same for all electrons. So this is important. Something what was before reserved for a single particle now becomes a macroscopic variable because it describes now the behavior of the collective behavior of set of macroscopic number of particles. And so we have the same wave function, which looks like for a single particle, but now it describes this big number of Cooper pairs. And then this phase and this is the density of Cooper pairs, rho. This can be shown that the current that runs in the system depends on the gradient of phase, for example, okay, number of the density of Cooper pairs, and there is also this vector potential here, but this is nicely described in the seminar devoted to superconductivity by Feynman in the last in last pages of the volume 3 of his lectures. But what we want to know is, since this looks like single particle, can it behave like an atom? Okay, so why we think that this could be a good candidate to observe macroscopic to observe quantum phenomena at macroscopic level. So by macroscopic object we understand this big ensemble of charge carrier, these Cooper pairs. Okay, so why we think that this could be a good idea? So we have this the same superconducting wave function which describes the collective behavior of many Cooper pairs, which is good. So formally it looks okay. This phase, because of this spontaneous symmetry breaking, is now a macroscopic variable. Importantly, the superconducting condensation creates energy gap in excitation spectrum. So we know superconducting gap, which separates Cooper pairs from interacting with environment. So this vastly reduces the environmental decoherence. So simply Cooper pairs, they don't want to interact with environment. They are very isolated. Like we can isolate atom, putting it in vacuum, which makes it also very interesting to offer as a platform for quantum computing, because the isolation is very good. Superconductivity is also nice object isolated from environmental decoherence. And then we can think that if we reduce this interaction environment, we can promote the presence of quantum effects even at big scale. The most perhaps widely studied object in superconductivity is Josephson junction. So here should be N also. Okay, so the Josephson junction, we have these phases on left and right side. We have two superconducting materials which are connected together through very thin insulating barrier. So Cooper pairs can tunnel, but single Cooper pairs, this is just normal tunneling at the microscopic level, can tunnel from one side to another. This is first Josephson formula. So the current that flows through such junction is proportional to the sign of the difference in phase between these two superconducting leads. For this, Brian Josephson obtained for prediction, this prediction, which was then confirmed. He obtained Nobel Prize in 1973. And this year Nobel Prize is actually for showing that this Josephson junction can be used like an artificial atom, that we can play all these games related to quantization of energy, tunneling, superposition of states, decay. So we can create artificial atom which can be engineered, whose properties can be controlled by us. So these are basically these two papers which lay the ground for further developments, but of course when such Nobel Prize is awarded, people they trace back to this moment that ignite a given study. So this was the moment at which this quantum electronics was ignited. These are two papers which followed one another on the same year. One is devoted to the tunneling. We will talk in a moment about it. And another energy level quantization in such junctions which are biased with current. Okay, here is some fabrication, so I can quickly go through this. For many of you it will be known. So how we can make such junctions. So we cover silicon substrate with polymer. We irradiate with electrons. We can break polymer into monomers. We use developer which etches away these monomers. So we are left with such cave, and now we can evaporate material. So it lands everywhere, also on the silicon substrate or other substrate. It also lands on the polymer. Polymer is removed in the lift-off process, and we are left with our structure. So more for producing Josephson junction, this is our mask. Okay, here, look here. So this is our mask that we prepared with the e-beam lithography, and now we do first evaporation from this angle. So we create these white strips. Then we oxidize everything to create this tiny 2 nanometers thick oxide barrier. And we do second evaporation, these dark strips. And here on the intersection of these two strips, we have Josephson junction. Okay, so this is, here is one lead of the junction, here is another, and here on the cross section, we have the junction. Okay, so this is junction that I did, okay, you see 13 years ago here on our e-beam lithography. But now we can embed this junction in electric circuit. This is the typical circuit which is considered. We'll call it resistively and capacitively shunted junction model. So this is junction which behaves like nonlinear inductance. This is capacitor. This is the bias resistor, and here is our current bias. So if I tell you that this is inductor, okay, and afterwards I can explain, if we have enough time, I can explain why it's, but it acts like inductance, Josephson junction. This is kinetic inductance related to the inertia of Cooper pairs. But if I tell you that this is inductor, you immediately recognize here the textbook harmonic oscillator, okay? So what is particular for such harmonic oscillator, that if we excite it, we can expect that we'll have the flow of energy from capacitor to inductor and back, so we have the oscillational current forth and back, yes? So we have harmonic oscillator. If it is classical one, we can consider that when we excite it, the amplitude of oscillation grows up. But if it is quantum, then we will have the only particular energy values will be allowed. So the question is, can we make it quantum, yes? But let's first, so I will follow how this was historically developed and how these Nobel winners came to the conclusion. If we measure IV curve of the such junction, current voltage characteristic, you will find pronounced superconducting branch, meaning that current flows but there is no voltage. Okay, this is the meaning of the dissipationless state. So if you try to increase this current at a certain moment, junction tells no, I cannot keep it anymore, and it switches to the non-zero voltage state, dissipative state. And here, if we bias it close to this point, in fact, it exhibits the stochastic behavior. When we will bias it with short current pulses, it may switch, but it doesn't need to switch. So we put junction in a metastable state, okay? So now we want to see the more physics of this metastable state. So what people do, they analyze the junction in picture of this resistive and capacitive shunted junction. Okay, here is the picture already that I explained. It's basically harmonic oscillator with this is nonlinear inductor. So here is you can either present it like this when it is current bias or voltage bias. You have either Thevenin or Norton equivalent. You can write the Kirchhoff law for this circuit. So we have the bias current is sum of three currents going through these three branches. So for this one, we use first Josephson formula, which I showed you some slides ago. Here is the current going through capacitor. This is the Ohm's law for resistor. So we put it together, okay? This is the same equation. If we put here second Josephson formula also, you start to see something similar to harmonic oscillator. So in the limit of gamma tending to 0, we can put this sign to equal sign gamma equal gamma. So we can map this equation into harmonic oscillator, and we can associate the capacitance with some mass. So this gives inertia of our system, and we can do kind of one-to-one mapping between harmonic oscillator and our system, which will allow us to think about the junction, oscillating junction, like we would have a fictitious particle with gamma corresponding to its position in real space. So for real particle, we have the harmonic oscillator equation with x coordinate, but here we have fictitious particle with gamma as its coordinate, but it behaves exactly as we would consider the particle in the real space. So we put this back to equation after. By the way, okay, you can find this lecture also on Kulfon webpage. So I gave this lecture, by the way, 14 years ago within modern lectures, modern problems in physics for students of Warsaw University of Technology, but at that time people were not so interested in this because it was not yet considered for Nobel Prize maybe. So okay, we look at this equation here, yes. So it looks like harmonic oscillator, but now restoring force is not the one resulting from Hooke's law, but it has, okay, this is just, instead of gamma you have such term here. But this is conservative force, so it's equal to gradient of potential energy. So by integrating, we get the potential energy of our system. You see cosine term and linear term. So this is tilted cosinusoid. That is why we call it tilted washboard potential. So the name comes from that there were in old times these washboards which were used to wash the clothes. And it looks like, if we look at it, okay, this is the tilted washboard potential. So now the point is that instead of considering some complicated, okay, just for it's easier for a human mind to consider the dynamics of such particle in the real space, but since mathematics is the same as for the behavior of the current oscillating on the junction, because here you have phase. Okay, we can say that analyzing this movement of the fictitious particle, we analyze what happens with current of the junction. So you recognize here the metastable state with local minimum. This tilt we can achieve with applying more current. Okay, here you see this is, if we apply larger current, we get more tilt. So if we keep our junction close to escape threshold, I mean it can be kicked out from this local minimum by means of thermal excitations, or if we consider allow for quantum alternative, this could be the tunneling. It can also escape even though it has not enough energy. But it has also this natural frequency of oscillation in the well. So in first approximation it is harmonic potential, but okay, you see it is to fully account for it is of course it's unharmonic. Okay, and now when we consider oscillation of such particle. We tell that this is in metastable state, so we can, by biasing with current, when its current is 0, that it's very well trapped in the minimum with well-defined phase. Well-defined phase means well-defined supercurrent flowing through the junction. If it is if the bias current is close to critical current, I mean equal critical current, then the local minimum completely disappears. So the particle cannot be stable anymore here. So the phase starts running by virtue of the second Josephson formula. Running phase means development of voltages, no more superconductivity. But here is this metastable state. So we keep this junction here at some defined phase value. It may this phase may oscillate, so current on the junction oscillates forth and back. And now we ask, what is the lifetime? How long it can live here? So this lifetime is described by Arrhenius formula. You should recognize here, okay, this is the attempt frequency and Boltzmann factor. So it compares basically the height of the barrier with the available thermal energy. If the thermal energy is high enough, the particle may escape through this. And this here you have write down the height of the barrier as a function of the bias current, which can be extracted directly from this RCSJ model which I presented you. Okay, so we want to measure now the lifetime as a function of this bias current. So there are, at least I know, 3 different methods. This is method that we use in our lab, and this was also used in one of the Nobel papers. But okay, it consists from sending many current pulses, each with definite amplitude, and in response to each, so what we do here, you see, we have this tilted washboard, and for a short moment we put our junction in a metastable state. So we give junction a chance to escape. So we create, we can investigate artificially constructed metastable state. We can investigate the escape in such system. So okay, so for a given bias current value, we count how many times junction was able to escape in response to, so we send 10,000 pulses and we measure that junction escaped 5,000, then we tell that probability for escape is 1/2. And this, of course, bigger the current, the bigger tilt, junction is less and less trapped in this local minimum, the escape is easier. And also, if temperature is higher, then junction can more easily escape, yes? So this is exactly an analogy to the throwing of a coin, yes? We flip coin, and we ask what is the probability to obtain head or tail, because the measurement of probability involved measurement over ensemble of exactly the same many experiments. And then this probability is related to the lifetime in this metastable state by this formula, which you can, okay, for example, the derivation is for example, in my paper which we made with Marek 10 years ago. So, okay, so we have this metastable state, so we can tell that this is decay of the junction to resistive state. So this is the analogy between the why people think that this behaves like an atom. So now what we can do, now we can measure, of course, this escape for this lifetime. Yes, we can measure this lifetime for various frequency at a given bias current. So what we do now, we tilt the potential and we apply microwaves, and we hope that we can resonantly activate this circuit, so we can make this particle bouncing forward and back more and more, and finally by means of the activation it may jump out. So here is the first experiment that this Nobel winners made. They sweep the frequency of microwaves across this system. So they injected not only they put not only the constant, I mean the current pulses through the junction, but also they were sending at the same time the microwave tone at a given frequency. And what they found, that at some particular frequencies, they found the enhancement of the, actually reduction of the lifetime with respect of the lifetime when there are no microwaves. And this reduction was reduction in lifetime due to resonant reduction in lifetime, okay? And from this they were able to extract, so you see this is the resonance curve showing that some particular frequency we are able to modify the response of the system. We can resonantly modify the lifetime, and this was interpreted as the enhancement of the oscillation in this circuit. But then the question, so at the moment, okay, this is classical circuit, yes? We could do it with classical inductor. But the question is following. We have this tilted washboard potential. Is it classical or is it quantum? If it is classical, of course, this particle can take any value of superconducting phase, any value of energy. It always has some well-defined amplitude. If it is quantum, then the phase becomes delocalized, and the localization of phase, look what it means. It means that the system, that our junction is simultaneously in the state in which a given value of current flowing through the junction is given with some probability. So we can say that we have at the same time many different values of current oscillating here, because this means the blurring of phase. Remember, phase gives us the current by virtue of first Josephson relation. Current is proportional to sine of phase. So blurring of phase means blurring of current. Current is macroscopic variable like superconducting phase. So can the wave function escape from a local minimum by tunneling? And R-church oscillation on a on Josephson junction, this is the abbreviation for Josephson junction, quantized in analogy to a harmonic oscillator. Okay? So what was the next experiment they did? This was explicitly mentioned in this Nobel decision. They measured here the escape rate out of the metastable state for different temperatures. And okay, and they found that at a fixed value of current, it's easier to escape for higher temperatures. Okay, this is kind of obvious, because okay, more temperature, more thermal fluctuations, it's easier to escape out of the metastable state. Well, importantly, from this fear of the thermal escape of this Arrhenius law, we can extract the temperature of electromagnetic environment. So we can see from the slope of this rate versus current dependencies, we can extract temperature. And for higher temperatures, they found that it nicely corresponds to the bath temperature, these three curves. But at the lowest temperature, they found that they are not temperature dependent. Okay, so now when we can plot the escape temperatures that they found as a function of the bath environment temperature. So we use Arrhenius formula, but now to fit this escape curves, we don't put here, okay, we just put here this as a fitting parameter, and down to say, okay, 50 milli this escape temperature corresponds to bath temperature, but then below it's higher than the bath temperature, and this enhancement of the escape temperature means that there is some additional mechanism. This was interpretation at that time. There is some additional mechanism which helps junction to escape. And then it was interpreted as this additional mechanism was interpreted as a macroscopic quantum tunneling. So this is the phenomenon by which the superconducting wave function, macroscopic wave function, switches from one configuration to another, or we can say that there is some quantum jump between these two configurations. Although energy separating these two configurations is too high to be overcome by thermal excitations, okay? So this was the first justification for the Nobel winners, this macroscopic quantum tunneling. Here is the important distinction now. Macroscopic quantum tunneling is not a tunneling of many Cooper pairs simultaneously across a tunneling barrier defined in a real space, okay? So we have, when the current flows through junction, of course, many Cooper pairs, they tunnel through. But this is not macroscopic tunneling. Macroscopic quantum tunneling is this quantum jump of the collective state of many Cooper pairs between two macroscopic wave functions, although the two configurations are separated by energy barrier which forbids the classical transition. So I repeated what I told a minute ago, yes? But this is important to realize. So now the second thing. Do we have quantized energy levels in this trapping potential, in this tilted washboard potential? If we have quantized levels, just think about atom, yes? We should be able to irradiate with photons and see some effects, yes? So what they did, now they biased with these pulses, they probed this metastable state, but in addition they irradiated with microwaves, and they were searching, so we expect that if we are able to excite our system from the ground state to the first excited state, the barrier thin by the wave function is now thinner and lower, so the escape should be much easier, yes? So can we see the resonance effect? Can we see that there are some chosen matching values of the photon energy which will give us the enhancement of the escape rate? And here is the result. So for 2 gigahertz sent on the junction and sweeping the current which was probing the junction, so by probing the tilt, look that when we tilt this barrier more, we open potential more, yes? When we open potential more, what happens? Okay, intuitive feeling gives us that the particle is less confined, the energy levels, they come closer to each other, yes? So when we tilt potential, we should sweep across the resonance condition. And this is what they found, that for some particular values of current, they found enhancement of the escape rate. You see? So this is that you see that when you radiate with 2 gigahertz and you adjust your picture, the landscape of energy levels to a proper spacing, you are on the resonant condition with impinging photon. So you go here, it's easier to escape rate is higher. Then when you lower current, you go out of resonance, but you get, now you can excite, because here is some finite temperature, so you have some non-zero population of all 1, 2, 3, 4 levels, even without excitation with microwaves. But when you excite with microwaves, you can pump the population on average higher if you meet this resonant condition, then the escape is easier. And then they found, okay, these 3 resonance peaks which they associated with 0, 1, 1, 2, and 2, 3 transitions, which will then well matched with the theory. Here's another confirmation. We can modify the 0, 1 energy spacing by tilting potential with current. For a larger tilt potential is more open and energy spacing is smaller. And now we can analyze, this is for transition 0, 1, that as we open potential more, so we tilt it more because current here is higher, then we see that the resonant condition is met at lower values of frequency, which means that the spacing is smaller as predicted by as predicted by theory. Simply, when we open potential, the energy levels they go close to each other. They go closer to each other. Okay. Josephson junction is a nonlinear inductance, so if somebody would like to know more about it, please approach me, but this is kinetic inductance. So this is the fact that when we accelerate the when we want to put Cooper pairs in motion, we need to give them certain momentum. They have some inertia, and this inertia leads to the kinetic inductance, which is seen in experiment like the usual magnetic or geometric inductance. And this is the inductance which we mean by the circuit which I displayed before. But this is nonlinear inductance, meaning that it depends on the current. Here it's depends on the phase, but if it depends on phase, it depends on the current. So it means that there are no equal distance between energy levels. Okay? So this, for people who do qubits, they know that it is very desirable condition not to have equidistance energy spacing. Okay, and this is, how many minutes do I have? 5 minutes, okay. So then, one of the laureates he's very famous for doing qubits. And okay, if you play with junction and you coherently drive it with microwaves, you can make the deterministic transition between 0 and 1 levels. If the junction is in 0 state, then the escape is more difficult. You need higher probing currents to see to measure the probability of the tunneling. If it is in this excited state, MQPT is more likely to happen, which means that the probability is shifted towards lower values of the probing current, biasing current. So this is way how we can distinguish whether we are in this state or in that state, okay? So this is maybe, okay, this is there's a real circuit, so I maybe don't have time to discuss it, but just to give you impression how the phase qubits 20 years ago looked like. Now there is different geometry, but this allows to do this microwave bias, also send the DC bias and some readout pulses through squid which is wound in gradiometric geometry. But I want just to go to scientific point that in this system it's possible to observe the coherent transition between 0 and 1 state, between ground state. So this is probability to be in the ground state, and when we apply the coherent drive on the junction, we can coherently go between these two states, involving all possible superpositions. Okay, so this presents that it's possible to obtain the Rabi oscillations, which is indication of the ability to treat it as a system which can be put in superposition of ground and excited state. And for this type of games, it's very important that these are not equidistance levels, because when we send resonant microwaves, we don't want to address transition from 1 to 2. We only want to stay here in between these two states. So here this can be, of course, imaged as a coherent deterministic evolution of the vector state on the Bloch sphere. So we go from 0 through superposition through to back to 1 and back to 0, and these are the first experiment that you do with any superconducting superconducting qubit. So why it's so important? Because now we are entering the promising moment at which many commercial companies are promising us that the delivery of first commercial quantum computer and superconducting qubits are perhaps first in the race for presenting first running computer. So this is the quantum computer operating on 60 qubits, which was published by John Martinis, one of the winners of this year's Nobel Prize in Nature, on which he presented that some very specific algorithm it's possible to perform computation faster than it could be done for any classical computer. Then IBM disagreed with him, but anyway, this was it is treated as a first presentation of the moment at which the quantum computer, how we call it, starts to compete with the classical technology of the classical bits. Here is, I just transferred from internet. This is the Google's quantum computer from this month, this year. So you see dilution refrigerator like the one I have with Marek in my lab, but this one is perhaps bigger. You have here many microwave lines with attenuators. Each such one line addresses 1 qubit. So you see it's tremendous technical engineering effort really to build computer which would consist even from 1000 bits. And considering the big error in doing single operation, there is still long way to really present the useful quantum computer, but this one consists of, I think, 100 qubits, but this is not specified whether these are logical or physical qubits, because usually for these computers you can have 250 of them physically, but then you have to build some clever error removing algorithm, which in the end make the device working as it would consist only from 7 qubits, for example. Yes, but this is okay. This is the last slide. So what I would like you to remember from my talk today, that the Nobel Prize was awarded for presenting the artificial atoms, so objects which show all phenomena which we know from the elementary quantum physics at the macroscopic level. So I showed you analogy. Decay of the alpha molecule from uranium is, for Josephson junction, it's escape from superconducting state. But this escape is tunable with applied current, temperature, magnetic field. This is the feature that with Marek in Coulson group we use as a very as knobs actually to present some sensor functionalities of Josephson junction. So we use it as a thermometer, as a magnetic field sensor, because this escape is tunable. Then I showed you the tunneling, which is observed for proton-proton or also for this alpha decay, is observed for the macroscopic ensemble of Cooper pairs. So the wave function described the collective behavior can jump from one configuration to another, although the configuration are separated with the barrier which forbids the classical transition. We have energy quantization. Think about Bohr model, but in the potential of the junction we have also such energy levels which can be put into superposition. Then we obtain Rabi oscillations. So this would mean that we have here not only each of these states, it consists of gives us some wave function describing the probability for obtaining some particular value of the macroscopic current flowing in the system. But this too means that we have superposition of these two states. So we can think that we have system in which at the same time we have two macroscopic coherent currents flowing. So we have at the same time cat which is dead and alive. So this is perhaps the biggest system presented up today which preserves the quantumness. Okay, so we have these 4 features, and okay, we are Coulson group, and if you want to know more about Josephson junctions, you are welcome to visit us in our lab. Thank you very much.
So thank you very much. So Maciej, it was very interesting lecture, and now your lecture is open for questions. Do you have any questions?
Thank you, Maciej. A very nice presentation. You have constructed very nice thermometer out of this. And on the other hand, you showed that this thermometer should not work because we should have quantum tunneling. Could you comment on that?
Yes, so I don't work at such low temperatures. Yes, so as this And also this quantum tunneling, yeah, so if I really would go down to the lowest temperature, like if they went here, it would, yes, it would saturate, yes, because I would not be sensitive to temperature. But you see, this junction is sensitive thermometer down to 40 milli. And in fact, this result itself, I think, would not be accepted as a convincing proof that is that really this macroscopic quantum tunneling exists. But then the experiments followed, and they showed this crossover at higher temperatures. So this result was confirmed in some other labs, and that is why we can, because otherwise for people who work with low temperatures, below 100 milli, we know that always we have problem with saturation of temperature. So even it is described in the in this extended note of the Nobel Prize justification that these effects could be interpreted as a simply not thermalized bath which couples electromagnetically to the junction. That is why you get flattening out instead of following the, okay, here is also the applied magnetic field, and they showed that they are indeed able to go down with the magnetic field to switch the junction from quantum regime to classical regime. Yes, but to answering strictly to your question, we work with diam nanobridges, which at the moment are sensitive down to 250 milli, so we only have thermal effects. There is no quantum behavior of this junction. So what we use, we use this effect of the decay of the from metastable state of the escape. So this escape is sensitive to the temperature.
Okay, do you have any other questions?
Okay, you showed this picture where you showed the example of macroscopic quantum tunneling, which is
this one, yes?
No, the next one. Okay, no. The one when you claim that it is not a single tunneling of single Cooper pair, but I mean this one.
Yes.
Could you give us an example? What is this distinction? Because I'm not sure what this means. In particular, my question is, if you have a Coulomb blockade and you get to a moment where you have negative resistance, it's known that it is a tunneling of Cooper pairs. Does that mean that this is macroscopic quantum tunneling or not necessarily?
No, this is that is not macroscopic quantum tunneling. So here the point is following. So with this charge box, the single electron box, you deal with the tunneling of a single particle. So here, this is the usual tunneling, or okay, which you are more familiar with is okay. This one, yes, this is tunneling. So we have one electron which has some chance to leak out through the barrier on the other side, yes. So this is but this is the single particle tunneling, and a macroscopic quantum tunneling doesn't require that some electron tunnels from one side to another, because we have some macroscopic wave function on this side, some macroscopic wave function of this side, and this wave function must change. So this describes this is the same phase, which is okay here, okay, which is common for all this big macroscopic volume, and here also for all this macroscopic volume. So when we have the this macroscopic quantum tunneling, the phase of all these Cooper pairs changes, but we don't need any tunneling here. So there is no tunneling here in the phase. I mean the real phase. This is the macroscopic quantum tunneling is the tunneling in the phase of superconducting in the space of the superconducting phase. Yes. So we have so we have single particle tunnels from one superconductor to another through the insulating barrier. Macroscopic quantum tunneling involves the change of the phase of all this wave function describing this big volume of material. Okay?
Okay.
Yes, I think I described it also. I prepared the synopsis for our web page. And this is also, okay, I tried to be I spent quite a lot of time to be very explicit what we mean by the macroscopic quantum tunneling.
Any other questions? Okay.
So let's keep to the picture again. On the left side from the insulator, you have a quantum system, right? Non-dissipative.
Yes.
On the right hand, you have non-dissipative
Yes.
quantum system. What it has to do with a cat?
So the phase which changes for this system here, it's the simultaneous change in phase for many Cooper pairs.
That's fine. That's okay.
Yes. So it means that so our macroscopic object is now the system which is built from many Cooper pairs.
No,
Yes.
this I have no problem. That's fine with me. But you started from that unfortunate Schrödinger's cat.
Yes, yes.
With all respect to all cats owners, we don't want to terminate any cats. Live cat is a dissipative system, just from the fact of being alive. The death cat, if you cool it to zero, is non-dissipative. So you don't have such a transition.
Oh, but this is, I gave the cat as a, because for Schrödinger this was not, there was some problem with that. So at that time people didn't realize these effects of environment. So it was, because we know now that big systems, we cannot observe the quantum effects because they immediately decohere due to interaction with environments which increases entropy. So it is irreversible. We cannot make swap forth and back. So if we made some phonon, it goes away. But superconduct, so then the question arose, okay, we were at some moment, we know that this is not reasonable to expect that cat is in these two states, but then the question that I posed, or which was posed by Leggett, but can we anyway extend the application of quantum mechanics to bigger systems? And then the superconductivity was pointed out as a system which very weakly interacts with environment because of this energy gap, and that is why they focused to look for this quantum effects in superconducting systems.
Yes, but then I can come to my question at that. If you want to do computation, you have to spend certain amount of energy for one bit of computations at the end.
Landauer limit.
Yes. So how does it match that what we have just been discussing, that you have a dissipative system?
Yeah, so I'm not able to answer this question. Because this is okay. This is something which goes too deeply.
I think here, if you want to have analogy is not quantum tunneling, but analogy are two states in the second part of the talk. So you have harmonic oscillator, and you have state number 1 and state number 2, and you have superposition of these two states, yeah, which you show by Rabi oscillation.
Yes, yes.
And this could be regarded one state as dead cat, another state as a live cat, and you make superposition of these two cats, yeah. This, I think, is analogy, not quantum tunneling. It looks to me.
Yes, this could be also, yes. Yeah, but this you could also say that, okay, the system, yeah, this can be, yes, both ways, yes, also for tunneling, but okay, this is maybe good, more appealing to.
And going back to Landauer, you do not have dissipation. You have dissipation only if you erase information. Yeah. So I think nobody is prepared to go into details, yeah, at the theoretical side. but you can perform all calculation without any dissipations, except if you keep information not erase. Yeah? A problem in our classical computation is that we erase information. Yeah? We just transistor and we change state and erase information which was before. You cannot come back to this information.
Yeah, but the point is that we are the erasing information in transistor is far, far away from Landauer limit, yes?
This is another story. So
yes,
the main dissipation which we feel on our labs, if we have computer, is due to just joule heating by wires. But I think that here I do not see contradiction, which Oleg mentioned. At least I didn't catch.
Yeah, but what was the contradiction? I didn't get the point.
He said that here is problem with dissipation, and I do not see what is the problem with dissipation here, I should say.
Oh, as long as you do this coherent swap between states, there is no problem, yes? Dissipation happens when perhaps you do readout, yes? So then it's a collapse of wave function and...
Okay, do you have more questions or comments? Oh, this one. So maybe
Bardzo dziękuję za tą thank you for this presentation. I just wanted to ask because at first glance it looks like in general superconductivity, as I understand, is a macroscopic quantum effect, non-dissipative in the sense. So it could be used for showing the quantum effects in a microscopic scale, but this method, like with involving Jozensov junction and so on, seems like a kind of non-trivial method, like a little bit a higher level of complication for me at first glance. Have people investigated before doing it in a simple manner, just maybe with quantizing the currents without the oscillation of currents, for example, that you just have a superconducting loops and they have currents and you just change this current. It's also a system where they probably have, you could read out the current afterwards and it could be conveying information, for example.
Yeah, so the point is that to have some quantization effect observable, you need to confine your system. And here I showed you this confinement potential, which is this CSJ model. And then if you have this confining potential, you have some, classical variable, which is current, which is the oscillation of current. And then because of this very weak interaction with environment, you can postulate that perhaps there are some levels there. But the spacing, the energy splitting arises as an effect of the trial of localizing the system to some, yes, so you have to put it into some potential and then like particle in the box. So this is what they did. They had this tilted Washburn potential and then I think that they started to think, okay, it looks like particle, so maybe the energy will also behave like the particle and which is confined in the box. So I don't know any Josephson junction is I think that I have not seen, at least in superconductivity, any other test bed that would be so useful as Josephson junction for presenting this type of physics. But you would need to come up with this potential first.
Thank you.
Okay, so thank you very much, and I don't see any other questions. Do we have any comments as well or not? If not, so thank you again.
Thank you.